Okay, let's start. A very good afternoon to everyone. On behalf of the organizing committee, I am Dr. Dinesh Day from the Department of Chemistry, and I am delighted to welcome you all to the second session of day 4 of the 5-day STTP and FDP programs on recent advances in intelligent systems and smart technologies for core engineering applications. It's my pleasure to introduce our keynote speaker for this session. Our speaker today, Dr. Vivekanand Sharma, is a distinguished researcher in the field of supramolecular porous materials. Dr. Sharma earned his bachelor's degree in chemistry from Deen Dayal Upadhyay, Gorakhpur University. He subsequently completed his master's degree in chemistry from University of Allahabad. In December 2013, he joined the research group of Professor P.K. Bharadwaj at IIT Kanpur, where he completed his PhD in supramolecular porous materials in 2019. He was my junior during my PhD at IIT Kanpur, and I have had the opportunity to collaborate with him on several research publications. Following his doctoral studies, he worked as a postdoctoral research fellow at the Smart Hybrid Materials Lab at King Abdullah University of Science and Technology, Kaust, Saudi Arabia, where he spent 3 years conducting advanced research. In June 2024, he moved to the IMAP group at Institute of Porous Materials, IMAP Paris. His current research focuses on metal organic frameworks and polymer composites for photocatalytic hydrogen production. Dr. Sharma has published more than 30 research papers in high-impact, reputed international journals, contributing significantly to the advancement of porous materials and sustainable energy research. Today, Dr. Sharma will be speaking on how porous materials are powering smart engineering solutions, a topic that is both timely and highly relevant. We are confident that this session will provide valuable insights and stimulate meaningful discussion. So before we begin, a few brief announcements. Please keep your microphones muted during the lecture. Feel free to post your questions in the chat box. We'll address them during the question and answer session. We kindly request your presence in case of any technical delays. So with that, it's my great honor to invite Dr. Vivekanand Sharma to deliver the keynote address. Dr. Sharma, the screen is yours.
Thank you, Dr. Dinesh Dey, for this beautiful introduction and mentioning the fact that I was your junior during our PhD at IIT Kanpur. So I am going to start this sharing screen.
Yes, you can share the screen.
Okay. Is it visible?
Yes, your screen is visible.
Okay. So, hello everyone, and I welcome to all of you, and thank you for joining us this afternoon for this talk. So I am Vivekanand Sharma, and I am already introduced by Dr. Dinesh Dey. So without any further ado, let's start today's talk, where I will talk about the porous material and the different kind of their categories and how in modern time they have enabled some of the more how the porous material can be connected with the current engineering background students and the research topics. So in this Like the whole short-term course is built on the intelligent system and smart technology. So am I asking that what do you understand by the intelligent system? So the system which can have a ability to sense, process, and respond accordingly, that can be classified as the intelligent system. So in modern day, scientists and engineers have created a lot of systems for which some of the examples I have introduced here. You can see like the smart watch. In the upcoming future, we will see the driverless car, which will be built on the AI and different Bluetooth technologies. And in our home right now, we use some of the smartwatch which tells of the temperature, date, and everything. So these are built on the surrounding system, which these system or instrument sense, process, and respond. So using this intelligent system, the nature has built the porous material billions of years ago, and before the human civilization. In fact, here are some example. You can see like the honeycomb, our some of the bone which has been like a network of the porous material, like the joint network of the porous system. Stone, soil, wood, coal, lotus leaf, and sea sponge, all are belong to the common classification, and we can call them the porous material. So using these natural substances, how our ancestors build up the some devices like not device, I can say like the system to purify the water. Here I have included a example. See, using these natural porous substances like uh, stones, coal, and wood. We have purified the water long time back. So this illustrates the example and the importance of the porous material. Now we have a lot of advanced filtration system using the UV treatment and some advanced filtration system. But this has all led the has been built on the foundation of the previously nature built porous material system. So now we have understood something about the porous material. So let's define like what exactly are the porous material. You can see the very beautiful analogy of the porous material with the sponge-like system. In all our household, we use some scrubbers or to clean our home utensil after cooking our food. So in a similar way, the yellow color boxes it represents the porous material. In there, like different type of or shape of the pores exist, and that pores can be utilized for the keeping the gas molecule for some gas molecule or some gas molecule can be passed through them. So maybe you are getting from that like what are the porous material? Like they have a hierarchy of the pores of different sizes. So now I have classified the porous material on the basis of two different things. The first classification of the porous material will be based on their pore size, like how big or small the pores, and the second classification will be based on their pore type. So let us understand the first one, the pore size classification. We have a different size like small, medium, and large pore. In a similar way, in the scientific terminology, we can classify them in the three parts: microporous, mesoporous, and macroporous material. So the microporous material or the microporous material have a size less than 2 nanometer up to the maximum 2 nanometer. Mesoporous have a size of 2 to 50 nanometer, and the porous material have a size beyond 50 nanometer of the size. So this is the classification based on the pore size. Now the second classification of the porous material is based on their pore type. Suppose we have a different porous material like A, B, and C, and we just can combine all of them. Okay, so there is a very natural thing that there will be exist a pore in between different material. So the pore which exist between the material. So based on this, we have classified them the two type of porosity. One is called interporosity or intrinsic porosity, and second will be the intra or that is also called a extrinsic porosity. So intrinsic means suppose Let's take example of human. If we consider like human is a porous material and we don't have anything from inside our body, so that porosity is within us, like it's not coming from outside. So that is called the intrinsic porosity. It means that material itself is a porous. But extrinsic porosity is that when we combine different substances with close to each other, so there is a vacant space created in between those material, and that is called extrinsic porosity. So now we have understood somehow the basic introduction about the porous material. So now we can start our today's agenda, where I will describe the three different class of the porous material and their real world application and their future perspective and your role in the current uh, technology invention. So the first is based on the metal organic framework. This is a first class. Second, I will talk about the metal phenolic network and subsequently move towards the organic cages. And in each section or the in each section of the porous material, I have included the example, like how they are like helping some of the core engineering problems of the modern society. Before introduction of the metal organic framework, might be some of you aware about this last year announcement about the Nobel Prize in the chemistry that has been awarded to the three professors jointly. Professor Susumu Kitagawa from the Kyoto University, Japan, Professor Richard Robson from the Melbourne University, and Professor Omar M. Yagi from the University of California, Berkeley, for jointly the growth and development of the uh, parallel research area based on the porous material, where these distinguished professors contributed a lot, and they have these materials are now in day to life coming and solving some of the crucial problems in our society. So, what are the MOF? Let me explain you. So, MOF is stands for the metal organic framework. So that is made up from the two components. One is called the metal, and the second will be like the organic part. So we can consider like maybe some of you have already know what is the molecular Lego in our childhood, or maybe so this is the type of toy where the metal nodes can be considered like this red color box, and this blue is like the organic linker. So they combine in a 3D way, like in three-dimensional space, and they are very harmonic structure, like throughout their structure expansion. They are very regular. So the special features of the MOF includes they are highly ordered, like they have a long range order of the same size of the pore size, like same order of the porosity. They are very porous, and their porosity is 10 up to 90% of their material. Like the MOF can be porous up to 90%, and they are tunable design. Like it is very possible to design a particular MOF for a particular application. So there is a fun fact about the MOF is that some of the MOF reported the very high surface area, and some of them, like only 1 gram of MOF material, have a surface area almost equivalent to a large football ground. Here I have shown some of the common organic molecule, which maybe you heard in your 12th or the high school studies about these linker. Like these are the organic backbone of the framework. So these are the only examples, and the list is 4 minutes long. So I have here only included a few examples. So the exogenous is like these are not the found naturally in our body or in animal or plant system, but the endogenous linker or the endogenous chemical which is naturally exist. Maybe you know about adenine, aspartic acid. These are the amino acid. These are all the DNA unit, fumaric, muconic, and gamma cyclodextrin. Gamma cyclodextrin you might be not heard, but this is made up from the sugar molecule unit, that is the glucose structure, where 8 glucose units combine in a cyclic way to form a gamma cyclodextrin. So let's talk about the real world impacts of MOF in modern technologies. Some of the examples I have included here, like chemical defense, anti-counterfeiting, green energy, volatile organic compound sensing. Let's talk about the example like anti-counterfeiting. It's like a technology which has been already piloted on the $120 million scale of the electronics material, where heterometallic, like two different type of metal unit has been utilized in that mob, and their fluorescence signal was very unclonable. Like it was impossible to clone their fluorescence signal. So that has been tagged on some electronic item so that the people or the industry cannot duplicate them. So these include the modern example of this metal organism framework. But let's talk about some of the currently going more worse problem of the global warming and the release of carbon dioxide. As we all know, aware about the global carbon dioxide emission because of the large industrial pilot plants exist in almost all the countries. Okay, and it is very difficult to control uh, their CO2 because it will ultimately halt or impact the production cost. So we need to devise a technology which can capture selectively only the carbon dioxide so that we can have a collection of the carbon dioxide, and that collected carbon dioxide can be utilized for some other purpose or can be uh, thrown into the sea, in the sea, like the bottom of the sea. So what happened at current technology, use the some of the amine solution, okay, for the capturing of the CO2, and that amine solution captures the CO2 converted into the AgRadine, and that chemical deposited inside the sea. But the problem with the current technology with the amine solution is that the very high regeneration cost because of the thermal heating, and also the corrode the container, like the container big size which we use in industry with amine solution, that will highly corrode the material itself and also the container. So we need to devise a material which can selectively capture carbon dioxide, and it can allow to other gases pass through them. So here are the impact, and we are getting the severe impact because of the heavy industrial evolution of the carbon dioxide or other flue gases. Because so we this results into the air pollution, lung health, and our daily day-to-day life, which has been severely affected. So there is a very cyclic relationship existing between the industrial development and our health. Okay, as we produce more and more, we are getting more and more air pollution. To deal and to tackle with this, the scientists from the Calgary, University of Calgary, Canada, okay, had developed a mop that has been named as CALC 20. So CALC is the acronym that is exists for the Calgary framework, and that has been developed under the guidance of the Professor George Shimuju. At the bottom, I have also shared the reference. I hope you can be able to see that. So from the synthesis point of view, it looks very simple to synthesize this mop. So, and in the subsequent slides, I will talk about this mop and the performance of the CO2 capture. So this mop has been synthesized very easily using the zinc oxalate as a metal salt and 1,2,4-triethyl as a organic part or organic linker. So in the resulting framework, we can see this linker like the triazole and the metal salt has been connected in the 3D dimension. Okay, and the oxalate unit, which is coming from the zinc oxalate, has been working as a pillar in between the different layers of the triazole and zinc. So, and you can also see there are some vacant space here, like this one here and this is also. So that is the space which has been harnessed or utilized for the CO2 capture. So first of all, these authors have performed the carbon dioxide uptake versus the nitrogen uptake. Like they have compared the CO2 capturability versus the nitrogen capturability of this framework. So we know that the industrial evolution, like the gas of the gases which is coming out from the chimneys on the industry, do not contain only the carbon dioxide; they also contain the nitrogen. Okay, so this is very must property a material should have, that they cannot capture nitrogen. They should capture selectively only carbon dioxide and allow the passing of the nitrogen. So from this graph, we can see at the lower pressure here at the bottom part represents the nitrogen capture, and this large curve, which is bending like this one, it for the CO2. So we can see at the lower pressure, like when the at the axis scale, we can see 200, 400 millibar. So at very lower pressure, we can see the nitrogen uptake is very little. It means that the material is not capturing the nitrogen at all. But at the same lower pressure, you can see here like the very high uptake of the carbon dioxide gas in compared to the nitrogen. So this was a very promising result, okay, because it was not this framework or this MOF was not capturing the nitrogen. It was capturing at the same lower pressure, carbon dioxide more, okay. So let's talk about the how the CO2 exists in between the pores of this framework. Here I have shown one pore, like, and the CO2, the red color is like representing a carbon dioxide molecule, which you are seeing the perpendicular to this my laptop screen. So this gives the three interaction point of this distant 4.68 angstrom and this one. So these are the smallest interaction exist in between the material where to stabilize the CO2. Also, the enthalpy of the CO2 adsorption is comes around 34 kilojoule per mole. So this energy was in the moderate range, not too much high, not too much low. The moderate range indicates that the favorable interaction of the carbon dioxide gas with the material, and also it also indicates the lower regeneration cost. Like it is not very difficult to take out the CO2 gas from the material. Once it will be material will be fully saturated with the carbon dioxide gas. Now, the authors have further tested the industrial durability of this framework, like in real condition, how this material behave. So you know that in a material, it's not like that we will apply just like 50 kg or 100 kg of material at the pilot plant or industrial site, and just after 1 month we need to remove the and to replace with the new material. We need a material which can survive for at least a couple of years, okay, without losing their performance. So at first one, they have performed the thermal regeneration stability, where the certain amount of the material has been utilized, and that has been the tested like the continuous uptake of the carbon dioxide and continuous regeneration of the same material. Like at one cycle, they have captured the carbon dioxide gas, and further they have regenerated by heating the material. So what happened? Once after the capture the CO2, they further heat the same material up to 150 degrees Celsius using the dry air, and they have regenerated the material further. So from this cycle, you can see the uptake and the regeneration graph value remains constant up to 30 cycle, but in real condition, they have tested this material beyond more than 4,50,000 cycle. So that indicates industrial level durability. Further, they have scaled up, like they have synthesized this material on very large scale using some industrial partner, and you can see the from this year either lab scale material or from the company's built up material up to 300 kg. All the materials give the almost identical values of the carbon dioxide gas uptake over the material coming from the different batches from the company, from the organic, from the different government organization or from lab. So all have performed the similar level of carbon dioxide. So this tells the industrial scalability, like this material is very possible to develop on a large industrial scale. So let's talk about the visual of CO2 capture and the companies involved in behind this metal organ framework. What happened? In a simple term, we have a material, something like that, which have a very hollow space, okay? We gave this flue gas. So flue gas is like the gas which is coming out from the industry that contains carbon dioxide, from water vapor, from nitrogen, and we get the final material here. So the flue gas is passing through this material, but nitrogen is coming out, but only the carbon dioxide, the black color, has been captured inside the pore. And further, we regenerate the material by heating it under dry air using 150 degrees Celsius temperature. So this MOF has been further patented by the that group using their own country, that is Savante, where I mentioned here. So Savante is a Canadian company, and for the rights exist with this company, and they have partnered with the BASF company. The BASF is the one of the largest chemical manufacturing company for known for their large supply chain. So they have partnered that, and now they are working together to scale up and to uh, develop this mop and to employ on the different industrial scale for the capturing of the carbon dioxide, and this is already under the production, and at some places they have already utilized. So now this was the story about the metal organic framework and their uh, recent advances, like how they are going to utilize. Now I will talk about the another class of the porous material that will be called as the metal phenolic network. So why I call them the nature's blueprint? Because the chemistry behind metal phenolic network is nature inspired, because the organic part, like in a similar like metal organic framework, this also contains two different component in their formation. One will be the metal, second one will be the phenolic. So phenols are the simple hydroxyl group, like the OH group containing compound. Okay, but why I call the nature blueprint? Because these phenolic molecule already existed in the all the fruits, vegetable billions of years ago, and nature has used these phenolic network in their own chemistry. So that's why I call them nature blueprint. So these are very versatile functional material. Some of the unique example I want to tell you about the phenols like that. Maybe if you definitely take day on the daily basis tea, coffee, or the red wine. Okay, so the taste or the unique taste you get once you have a sip of tea and coffee. So that is the tannins present in those like the phenol. Tannin is a type of phenolic compound. So that reacts with our mouth buds and that gives a unique taste. So what here are the some examples of the naturally found uh, polyphenol. You can see like the tannic acid present in the tea and coffee beans. Some are the allergic acid, gallic acid, pyrocachicol. So these are the some hydroxyl containing. Like you can see why I call them polyphenol, because the number of OH group are more than one in all the molecules. So the synthetic chemistry of the metal phenolic network is very simple. Just take some polyphenol in the appropriate solvent, mix up with them metal solution, and within a second to within an hour, you will get your metal phenolic network. So in this study, I have utilized in our collaborator from the plant science, like how metal phenolic network can be utilized as a sustainable tool for the precision agriculture or the sustainable agriculture. So first of the question is that what is the need of the sustainable agriculture? So I'm pretty much sure like all of your background has been from the somehow your background has been related to the agriculture, and you have seen in your childhood or maybe your father using some of the fertilizer for your own agriculture, maybe in the wheat plant or the rice or any other type of the agriculture part. So most of the fertilizer we use, it doesn't utilize fully, and almost 70% of the global crop yield losses because of these don't work with the full potential. And as in our daily life, we feel some of the stress, be it the financial stress, social circle stress, or the career stress. In a similar way, plant also feel stress in terms of the salinity, UV visible radiation outside, the drought, like the absence of water, extreme temperature. So these factors collectively called the abiotic stress. Like these are the non-living things like drought, UV radiation, salinity, extreme temperature. So that's why we call them abiotic stress. So we need to develop a methodology which can be utilized to help plant or any agricultural field so that they can survive even under the very high stress condition. So as a part of that, we have taken the kinetin. So kinetin is a well-known molecule in the agriculture field that is well known for the plant cell growth and development with the better retention of their bioma. So we have chosen the kinetin as a guest molecule, and how we can capture that gift like kinetic molecule in a porous material like metal phenolic network. But what is the need? The need is that because the kinetin itself was not that very much stable, it has a poor water solubility. Okay, the kinetic molecule is not stable under the outside under the sunlight. Okay, and it also very easily degrades when we give directly in the our field to the certain plants. So we need to protect the plant, but before that we need to protect the kinetin. So here is our approach. We have taken this molecule. This is called a caffeic acid. Here I have mentioned, and we have taken the zinc sulfate. So caffeic acid is a type of polyphenol because see, you can see here if I have more than one OH group, and we just mix up them both up the caffeic acid and zinc. And during the mix up process, I have added the kinetin into the solution, and that kinetin has been captured around that has been captured in between the porous space of this metal phenolic network. So I have presented that metal phenolic network as with the presence of kinetin here, and we have studied their size from the TEM study, that is the transmission electron microscopy, and from the TEM we get to know that the size of these particles of the metal phenolic network is around 100 to 150 nanometer. That was very, very small. So further studies indicate that this and the formulation, like I forgot to mention, we named it CAF gene. For CAF gene K, CAF is for the caffeic acid, gene for the zinc, and K for the kinetin. So when we have studied this, so we have found that this formulation release kinetin, okay, when the irrigation system, like the water outside have seawater, like when we have irrigated or given the water from the seawater, that release kinetin slowly over the certain time. In a similar way, we have also studied the effect of pH on the kinetin release. So at faster release, we have found at low pH, like when the pH is acidic of the medium, like the surroundings pH is acidic, for this formulation or this network will release the kinetin more fast. But when the pH will be basic, like beyond more than stable, for this formulation we release kinetin very, very slowly. So this is going to help a lot because in our India, the soil pH varies from region to region. Some has the acidic and some has the basic pH. So what we did, we have taken a tomato plant as our like model plant, and we have studied the release of this kinetin on the for the tomato plant. So what we did, we have taken few certain number of the tomato seeds, okay, and that seed has been dipped or soaked overnight, okay, into the or formulated solution like the calf gene K. In a similar way, at our home, sometimes we soak chana or any type of dal, okay, overnight. In a similar way, we have soaked tomato seeds into our formulated this into the solution of this calf gene K, okay, for 12 hours. What happened during this soaking process? The tomato seed has captured some of the this calf gene K nanocarrier, okay, some has been stick on the wall of the tomato seed. So when we have when we have potted them in a certain like the pot for 1 week, we have found that that the pot which contains the calf gene K nanocarrier has shown the longest growth of the root, okay. While in compared to the control means like we have not given anything to that seed. In one experiment, we have given only the kinetin. In another experiment, we have given only the calf gene, but that was not encapsulated with the kinetin. And the fourth experiment, we have given the nanocarrier, but containing the kinetin. So after the lot of study, we have found that the plant or the tomato plant which has been soaked with the calf gene K nanocarrier has been shown better growth after 1 month of the duration, and their overall their length, their biomass, like the dry weight, all was a lot better than the untreated plant. So basically we answered the question like, can plant survive salt stress better with a smarter treatment or not? And we have found at the fundamental result, which I have shown at the bottom, the uptake increases, like the kinetin uptake by the tomato plant was increased 3.7 times in compared to the without treatment. So here with the nanocapsule, like with our formulation, the kinetin goes into the plant by 1.54 microgram per ml, but without treatment, the kinetin uptake for the tomato plant was only 0.41 microgram per ml. So almost when we divide this 1.4 by 0.41, we give 3.7. So it indicates that once we have encapsulated the kinetin into the metal phenolic network, the plant was more able to take that kinetin, okay, and that kinetin helped them to survive the plant even in the extreme temperature, extreme drought condition, or the better, or in the presence of different complex medium. So this was the summary up to the like how this porous material has helped in agricultural sector to survive plants better with their treatment. And in another study, which I have not shown here, we have studied the similar type of approach on the capsicum, that is the Simla mirch, okay, plant on the mark level, and we have produced them the large production of the capsicum when I was in the coast. So this was the story up to the metaphenolic network. Now I will talk about the another class of porous material. So until now, we have seen that application of MOF and metal phenolic network. But how this section is different from the rest of the two material is that metal organic framework and the metal phenolic network all are like the polymer, like the 3D structure which is extended in the space. But here in this section, we have used a single discrete molecule to that was porous. So the question is that can we direct the empty space like the porosity so that we can sense something, some gift molecule without doing anything. So this is the question. And so before uh, giving me the introduction of this type of molecule, let me explain a basic fundamental like how we have designed this material. So suppose at one side we have a random distribution of the pore size, like the different size of the pore. Here I have shown some large circle, some are the small circle, some are the medium size circle. So these are all indicate the different porous material, okay, but with a different size, and they are randomly arranged. At one side, we have a similar size of the porous material, and they are like highly directionally arranged. So if we pour water molecule on both system from the top, so we will see the system which are randomly organized will have a different directional flow of the water molecule, while the system which have a very well aligned and the water molecule which like go through a like a directional channel. So inspired from this type of foundational knowledge, we have developed a material that was a porous, okay, but that was a discrete molecule, like it was only not a polymer, it was a single molecule which was porous from inside. It's like a cage structure. Here it is a cartoon representation of the cage, and the actual molecule is like this one. So you can see this cage is, there is nothing, there is only blank space inside the material, okay. So we have utilized this chemistry, very fundamental chemistry, that is called the shift-based condensation, okay. So using this molecule and this molecule, we have utilized synthesized this cage. So the unique features of this cage was that this was the impulse of the NH unit and impulse of the oxo group O, okay, from the top and bottom. So you might be know that the hydrogen bonding. So these molecule is very well known for making a very strong hydrogen bond, like the NH group, fluorine group, and oxo group. They make a very strongest hydrogen bond. So based on this hydrogen bonding concept, we have designed a humidity sensor, okay, by taking two interdigitated electrode like this representation I have shown, and in between this space we have drop costed our the synthesized solution, cage solution, that is the molecule solution, okay. And after heating it for one few minutes up to 70 degrees Celsius and under vacuum for 24 hours at 100 degrees Celsius, finally we get our humidity sensor. So, and in this graph, I have shown how the resistance, ultimately we can say the conductivity, so how the resistance change with the relative humidity. So, because you know that this cage has a high number of NH and oxo group that can make for very good hydrogen bonding. So, in this graph, you can see this cage has shown very high resistance, like the very low conductivity. Okay, in absence of any water molecule, like when there was no hydrogen bonding, this cage material was insulator, behaves like an insulator. But when we change the surrounding medium and we have added a lot of water vapor in the system, so the relative humidity goes up to the 95%. Okay, so when the relative humidity goes up to 95%, we have found the very sharp decrease in the resistance. It means that the overall sensor become very, very conductive, and it was conductive over the duration. Here we have plotted this resistance versus time graph. When we change the relative humidity, again from 95% to 11%, it means that there were very few water molecules present surrounding the sensor. So in absence of water molecule, like now I will not say molecule, I will say the vapor, because these water was present in the form of vapor, not in the liquid, not in the solid form. So when the relative humidity changed from 95% to 11%, so the sensor becomes insulator, and its resistance becomes suddenly decreased and goes maximum up to this one 200 mega ohm. So this represents that the response and recovery cycle of this sensor. So it was very pretty fast, like sudden decrease and sudden increase of the their resistance. So based on this, we have thought, can we design a sensor like touchless sensor which can sense water molecule from the living objects or not. So using build up on this foundational study, we have prepared a touchless humidity sensor. So let me explain the mechanism of this sensor. What happens once the sensor have an organic cage molecule that have very high number of the hydrogen bonding site. So it sends water vapor surrounding them, and these water molecules make for hydrogen bond with the cage, and that hydrogen bond percolate, means is spread in the directional way, and that allows the conductivity to read out, and ultimately we read out the resistance from that sensor. So the next question was that let's summarize the performance of this developed sensor. This sensor was surpassed all of the current reported humidity sensor utilized in our day-to-day life, and the response cycle, like from the insulator to the conductor, it was only 70 milliseconds. It was very, very fast, even less than a second, just 0.07 seconds. And in just 158 milliseconds, it becomes conductive to non-conductive, that is called the recovery time. So it was hugely ultra fast. It was also stable. Okay. Over, like we have tested this stability for 6 hours at 100 degrees Celsius. It means that this was stable at high temperature also. Humidity tolerance, we have studied, like we have continuously keep the sensor for 36 hours in the very high humidity, 95%, and the sensor doesn't degrade its performance. Also, we have tested the same sensor after 6 months, okay, and we have found that the sensor was behaving as like before. It means that the shelf life of this sensor was more than 6 months, definitely. So the question was that, can we utilize this humidity sensor to touch something and to know that whether the water molecules are present surroundings or not, and how we can do that. So we know that our human skin or our human body continuously emits water vapor. Or not only our human skin, even the some fruits, vegetable, all have some moisture content. When you keep them inside the fridge, okay, they remain fresh for the longer duration. But when you keep them outside, okay, in the sunlight, they become easily dry and rotten over the time. So based on that, we try to know that whether this humidity sensor can touch the presence of fingers or not without even touching. Let's see this video and then I will explain how it works. This is the sensor. Okay, and when we bring our um fingertip closer to the sensor, so the resistance drop very sharply, and when we bring them far, resistance increases again. So it means that the continuous cycle of the resistance change up and down. Okay, so when we bring our fingertip close to the sensor like this one, so the water vapor which is coming out from the our fingertip is sensed by the same sensor, and its conductivity become increases, or you can say the resistivity becomes suddenly down. And when we remove our fingertip from the sensor, so its conductivity remains again down, or maybe you can say the resistivity increases a lot. So this experiment proves that this sensor was able to present even in the very trace amount of water vapor or the biological water vapor from the human skin. So we thought that let's expand this study to know some other fundamental application in our modern society. So we have taken asthma detection as a challenge. So why asthma was a serious problem? That it indicates that in India, more than per day, 548 patient dies because of the asthma, and even there is no medical emergency also. That also includes the patient which have a asthma problem that limits their physical limits. They cannot go, they cannot run outside because of their lungs issues, and sometimes they need medical treatment immediately. Okay, and unfortunately, most of the deaths occur, like nearly 50% of the death occur because of the not reaching the medical facility on time. So we have thought, can we develop sensor, okay, which can monitor their continuously the breathing pattern, like they exhale and inhale the air, and that can be detect or can see their breathing pattern from our mobile phone, and we when we will see any unusual breathing pattern, we can directly or very immediately we can reach up to the patient. So how we can do this like we have installed this humidity sensor, okay, inside the mask, the face mask. Yeah, okay. So you know that the when we inhale air and when we exhale air, so the air which is coming from our inside that have a more moisture content because that is coming from the lungs, and that will have a high moisture and compared to the inhaled air. So the normal breathing pattern, so we have plotted the normal breathing pattern with respect to time. So you can see the sensor have a continuously resistant down and up performance. But when a person or a patient can get asthma attack, their breathing pattern will change severely, okay, because of the different moisture content, okay, found in their exhaled breath. And so this will feel like a suffocation for the patient, and we can detect that suffocation, like that the moisture content which is coming from the patient as a exhaled air. So we can read out those signals using our Bluetooth connected phone, and we can monitor the patient asthma attack remotely, and immediately we can reach up to the patient if that or he or she needs any medical treatment or not. And also we can build up a cloud storage for that also, so that we can track all the breathing pattern from the last couple of months, okay, so that we can talk to doctor before about all the symptoms. So this humidity sensor we have used as a asthma tracking sensor for the asthma patient. Similar way, when we go to the any supermarket and we buy any vegetables or the fruits, so we first check whether the fruit or the vegetable is fresh or not. So using this sensor technology, like with what we have developed, we can easily know just by uh, like moving the sensor closer to the fruit or vegetable, and the signals we can read, and from this signal we can know that whether the fruit or vegetable is fresh or not. So what we did in this experiment, we have kept we have taken three apple. here in the first graph, this apple was kept inside the refrigerator. The second apple, which was kept inside the room, roughly at around 25 degrees Celsius. And the third apple we have kept outside in the sunlight. So it is very natural. The apple which will be inside the fridge will be fresh for a longer duration. The apple which will be in the room will be like have a moderate effect of the freshness, and the apple which will be outside in the sunlight have very little moisture content on their surface. So we have tried to build up a relationship like how fresh the apple is by using this humidity sensor. So the apple which was inside the refrigerator has shown the continuous and a similar level of the resistance changes and resistance down and up performance. But the apple which was inside the room has not that much down the resistance, and the apple which was outside in the sunlight has very little moisture content, and that has shown very low, like very less decrease of the resistance. So this indicates that the apple which was outside has almost no freshness, while these two apple have high freshness. So we have developed like a sensor which can be utilized to fruit freshness. So this was all the application about the metal organic framework, metal phenolic network, and the organic gauge. So let's summarize all of these studies. So what we have seen here today, from we have studied or we have seen a mop for the carbon capture. We have also studied the metal phenolic network that can be harnessed into the smart and the precision agriculture. We have developed organic cage for the precision humidity and gas sensing application. We have also seen how the sensors can be used for the non-invasive health monitoring. Okay. So these are the, so there is a very basic thing, maybe it may be coming in your mind, like what will be the future of this porous material. So you can see the future of porous material here. So the some of the meta organic frameworks are already have been utilized on the pilot scale, okay, on some industry, especially in the US and the Canada, and some part of the Europe, for selectively capturing the carbon dioxide gas using the metallurgical framework. Since the AI has already in the taking the role for the next generation technology, so we can use AI to know what type of porous material we can build for the better application. Similarly, the next future is the precision agri-tech. Like in the agriculture, we are going to utilize more and more advanced technologies, and also we are going to monitor our health by using such type of wearable health sensor. So what will be your role in this development of the science and engineering? You can work as a bridging pull between the science and the engineering, and you can take the inspiration from the modern discoveries and how you can utilize these basic fundamental scientific discoveries to turn out their application based on your engineering. So first study the chemistry foundation, like how physics, chemistry, and bio works. Okay, then it comes the material development, and then it comes to the engineering application, and it is your imagination how you can take all those molecules or those principles to devise or to generate or any application that will impact your societal relevance and your societal presence. So now the take-home message is that explore further and think differently and build what matters for the society. So with this, I'd like to take off for today's presentation. Now it's time for question and discussion. So let me acknowledge for your attention and thank to my all the collaborators and the contributor for the studies we have done together. A special thanks to Dr. Dinesh Day, Department of Basic Science and Core Engineering Chemistry, Bengal College of Engineering and Technology, for the kind invitation and support. Thank you all.
Thank you, Vivek. So now the session is open for any questions or any queries. If you have any kinds of queries or questions, you may ask to Dr. Sharma. Okay, I think there is no questions, but I have one queries.
Yeah,
Can can you go to CALF MOP 20 slide?
okay, Calf 20 mark. Okay.
Yeah, yeah. That is very interesting.
Yes, yes. Here.
Yes, yes. So this MOP can be utilized for the absorption of CO2 molecules, like
Yes,
right?
yes, yes.
Okay. So my queries is that we know in nature plants
Yes,
can convert the hazardous carbon dioxide to very important compound, that is glucose. Can we similarly convert this adsorbed CO2 in this MOF into some other valuable
yes,
compounds?
yes. Yes, they have utilized this like absorbed CO2. So we can have do two things. Whether all the collected CO2 can be expelled or collected at a single tank, so that we will have a pure CO2, and that CO2 can be utilized for making some other useful material, or we can discard those CO2 collected molecule, okay, under the geographical stones inside the sea.
Okay, okay, thank you. So if anyone is having any queries or any questions, you may ask. Okay, if there is no more questions, I would like to extend my sincere thanks to Dr. Vivekanand Sharma for delivering such an insightful and informative talk on supramolecular porous materials and metal organic frameworks. We truly appreciate your valuable time, expertise, and the knowledge you have shared with us today. I would like also uh, I would also like to thank the participants for their active participation and engagement throughout the session. And with this, we conclude day 4 of 5-day STTP and FDP programs on recent advances in intelligent systems and smart technologies for core engineering application. We look forward to your active participation in the upcoming session. Have a wonderful day ahead. Thank you. Thank you very much.
Thank you, Dinesh.
Thank you, Vivek, again.
Okay. So, okay, I'm signing out, leaving
Yeah,
the
yeah.
session. Yes, okay.